Okay, so as we said a minute ago, how do we tell how far away something is in space? I had you guys stick out your thumb and shift from eye to eye. And you can see your thumb seems to shift in accordance to things that are really far away. Right now I'm holding my thumb out and it's going back and forth on either side of the window. Okay. If I pull my thumb closer, then that shift is greater. So the closer an object is, and this is one of the questions that is on the assignment, so listen carefully to this. The closer an object is, the bigger the shift. Okay? So when I proposed this to you guys earlier, I said that if, what's a good color for stars? Red? If these are some stars that far, far away in outer space, that's a star. Can you guys believe that's a star? There we go. There we go. So here's some stars way, way, way in outer space. All right. And there was some sort of object heading towards the Earth. Let's say it's an asteroid. Does it look like an asteroid? And it's heading towards the Earth. How could we figure out how far away it is? Well, we could use that stellar parallax, which if from the Earth on this side of the Earth, if we had a telescope maybe here in North America, and we were looking through that telescope at this object, and we took a picture of it, what we would see is this object in the field of view of these stars. So let's say that these stars, when we took a picture of it, these stars looked something like this, all right? So this object will look like it's right here. All right, so this is from this telescope. All right. If at the same time, so this is North America, maybe there's a telescope over in Mongolia, the opposite side of in Asia somewhere, and you took a picture, they took a picture of the same object at the same time, then that object's going to be over on this side. So this picture would look something like this, where you would have one. Notice that the stars are fixed, so I'm trying my best to draw this and this. It's like the same picture. However, the asteroid would be over here. That's not a smiley face, it's an asteroid. There we go. The asteroid would be over here, all right? So there would be a shift. It would look like, if we superimpose this picture on top of this one, like this asteroid had moved this much from eye to eye. Okay. What we can do from there is we can figure out if this is the center of the Earth, how far is it to the center of the Earth, and look at this distance right here to determine what angle is this right here. If we know this angle, and this is the kind of Greek symbol for theta that tell us the angle of something. If we know this angle and we know this distance, we can use basic geometry to figure out this distance right here. And this was called stellar parallax. Now, if you guys remember the guys I was talking about, the sword fight, the guy getting his nose chopped off, and then the other guy that didn't like him at all, but they worked together. They didn't have a telescope. They were just looking at objects in the night sky, and this is what they determined to figure out how far away something like, say, Mars is using that concept. All right? All right, I'm going to dive into this a little bit deeper. Do we have any science fiction nerds in here? Nobody liked the movie Star Wars? You like the movie Star Wars? Do you remember how fast the Millennium Falcon is? How fast was it? He bragged about in Star Wars. The fastest piece of junk. Well, he actually bragged about it. He said he did the Kessel Run. And 12 parsecs. And that's supposed to be fast. But we learned that fast is a measurement of speed, right? How far he goes divided by time. What we're going to find out is that George Lucas didn't know anything about space when he wrote this movie. Maybe he knew something about space, but this is not a statement that actually makes sense. So what do I mean? What's a parsec? A parsec is an actual thing. It's not language that they made up for Star Wars. So what I want to do is start today. The topic of this conversation is find a pretty color to write in. We'll start with green. How to determine the distance of objects in space using stellar parallax. By the way, the word stellar just means stars. If you see the word stellar, that means stars. Okay, so how to determine the distance of an object in space using stellar parallax. All right, so before we go anywhere, the first thing that we have to do is find a new and exciting color to use. Step one, we need to review a circle. Why do I say review circles? Once again, the school district assumes you guys have learned everything that you need to know coming into this class. I've discovered that's not always true. You need to hang on as best you can. Okay. All right, so we're going to review circles here. What we have, let's draw a circle here. Basic things that we understand. We could take a circle and divide it into parts. Each part is called a degree. And how many degrees are there in a circle? There's 360 degrees in a circle. So if you could imagine, if this is a circle, we would go around and there is 360 degrees. And the smallest amount of degrees we can get to would be a 1 degree. Make sense? Except we can get smaller than 1 degree. We can get half a degree, right? Or we can get a half a degree. So first thing what you guys need to realize when we're talking about circles is that it's not a circle has 100 degrees or 1,000 degrees or 10 degrees. And usually if you see something like 10 or 1,000 and that's the whole thing, that means you're going to be able to break it down evenly by 10. So you can divide by 10, multiply by 10, and just move the decimal point. Circles aren't like that. Circles have 360 degrees. So we're not going to be able to take like half a degree and just say, well, okay, then that would be 0.5 of a degree. We have a different system of breaking it down that's going to sound like something that you've ever heard of before. So if we take 1 degree down, 1 degree on a circle can be broken down into 60 parts. These 60 parts, and we usually put a little tick mark like that. So 1 degree broken down into 60 marks, that little tick mark, that means minutes. we're not talking about time, all right? A minute is a division of 1 degree a second. So 1 degree a second, 1 degree of a circle would be considered 60 minutes, all right? Each minute, 1 degree, one minute can be broken down, and you can probably almost guess what this is going to be. 60, 2 little tick marks like that, stands for seconds. Okay. Now, agree that if I did something like this, you guys would say I'm making an arc in the sky, right? That's an arc. All right. An arc is just part of a circle. So every time we're talking about a part of a circle, a slice of a circle, we're talking about an arc. So instead of calling these seconds, you know, maybe 1 second would be called 1 arc second. Okay. So 1 arc second. So yes, to the question that was just asked, for those people who have actually done the geometry where you've done sine, cosine, tangent, cotangent, we are getting to that point. I'm going to avoid having to solve for those angles for this assignment, but really that's how it's done. All right, so going back to this, if you are planning to be an airplane pilot, if you're planning to have a boat or pilot a ship, if you plan on traveling, if you're a hiker like I am, you probably need to know what longitude and latitude is. And this uses this idea with the circles. So if we take a look at the Earth, does anybody remember what the equator's latitude is? The latitude at the equator? Interesting. 0 degrees is the latitude of the equator. Okay? Latitude, remembers, are the lines that travel north to south like this. They travel east and west. They tell you how far north and south you are. The North Pole, that's going to be 90 degrees. Where did they get 90 from? Where did they get 0 from? Well, if we look at from the center of the Earth and draw a line across the equator, there's been no change in angle. If we go from the center of the Earth and go perpendicular to that, that'll be a 90-degree angle, which means Seattle, which is about 47 degrees north latitude, so about this latitude right here, that means that we are at a 47-degree angle from the center of the Earth. All right. Now, let's say that you're in an airplane, you're in a pilot, you're in an airplane, you're flying over the ocean. And all of a sudden your airplane stops working and you go to crash, but a crash in which you could survive. Now you're in the middle of the ocean. How do you let people know where you are? Well, you tell them your latitude and your longitude are the lines that kind of go up and down, and it's based on the same idea as latitude. So what you would do is I would say, well, I'm somewhere in the ocean. And by the way, how would I say I'm in the middle of the ocean, Mr. Lee? It's not like my cell phone works. Well, it does. It actually could save your life. The newest iPhones, iPhone 14, have an SOS signal, which means that if you're crashed in an airplane and you're lost in the middle of the ocean, you can aim your phone literally at a satellite. Unfortunately, 14 is the first time they can do this. You can aim your phone at a satellite and send a brief SOS text message. So your SOS text message might be, this is my exact longitude and exact latitude. So you might say, I'm in the middle of the Pacific Ocean. I'm at 180 degrees west. That's a bad one. 80 degrees west and 23 degrees north. Great. And your phone would actually tell you that. If I ask Siri, what is my longitude and latitude? It actually comes up and it will tell you what your longitude and latitude is. All right? Because it's built into the phone. So I can figure this out. However, that means that you're somewhere, and it's like a 36 square mile box that you could be in, depending on where you're at in the globe. That's a pretty big area. If you're in a little life raft floating in the ocean and somebody flies over that longitude and latitude, they're looking at a 36 square mile area. It's hard to see. So what you can do is, and your phone can do this, it can break it down into minutes. Well, that's going to get it down to maybe about 6 miles, and then down to seconds. In fact, your phone actually breaks it down to fractions of a second of longitude and latitude, and that's how it knows where you are exactly on a freeway. What does this have to do with stars? I just wanted to show you guys that 1 degree of a circle is 60 minutes. Can be broken down into 60 parts called minutes. 1 minute can be broken down into 60 parts called seconds, and we're talking about arc seconds. All right. So that leads me to step 2, is what we talked about already. The second thing we know is, how do we look at faraway stars? How do we look at faraway stars? This is a little bit more problematic because if we were talking about an asteroid, I said we could just take a picture from either side of the Earth. But what if here are the stars in the background? If we're looking at something maybe outside of the solar system, maybe another star that is light years away from us. And by the way, a light year is the distance that light travels in 1 year. Light is not instantaneous. All right? When I turn on a light, yes, it fills the room up immediately because it travels really, really, really fast. But it does take time to get from one place to the next. For example, right now we're looking at sunlight. The light that you're seeing outside shining in is the light coming in from the sun. It took about 8.5 minutes for that light to leave the sun and reach the Earth. Which means when we're looking at the sun, we're not looking at the sun as it is right now. We're looking at the sun as it was 8.5 minutes ago. If the sun suddenly blew up, we wouldn't know for 8.5 minutes because we got to get that light to come to here. So the next closest star to us outside of our own sun is about 4.5 light years away. I think it's 4.8 or something like that. Which means we're not seeing that star as they are now. We're looking at a star that was there 4.5 years ago. We're seeing that star as it looked like 4.5 years ago. It just took 4.5 years for that light to get here. If there's a planet on that star and it's looking back towards the Earth, what they're seeing is an Earth in which Donald Trump is still president because they're looking at the light that we sent off 4.5 years ago. All right? So, how do we look at, let's say we're looking at a star, let me use blue, that maybe is somewhat close to us. How do we determine that? So these are really far away. Far, far away. So we're talking like, you know, when we're doing the thumb thing, those trees far away from my thumb, that type of thing. So those stars are far, far away. Here's the Earth, and there's the sun. Does orange show up okay? Okay, with this. So here's the sun. All right. We live on the Earth. Let me use green for the Earth. Here's the Earth right here. And if we took a picture of this star, that star would look like it's right next to this star. So if we took a picture, making a mess over here, of the stars in the background, just like what I drew before, that star might look like it's right here. Now, it's not going to make much sense to have in this case, a camera on this side of the Earth and a camera on that side. They're almost too close together to determine something that far away. So what do? Well, we do orbit the sun, right? So if we go over to this side of the sun, how long would it take us to get over here? Anybody have any ideas? For the Earth to go from this point, from point 1 to point 2, how long would it take? Good, yeah, half a year, 6 months. So if we took a picture of that star 6 months from now, that star's not going to go anywhere. If we took a picture of that star in January and then came around and took a picture of that in June, then what we would see is now that star looks like it's closer to this star over here. So now that star looks like it's moved. It's shifted from being here to over to here. So we have that stellar parallax going on. All right. All right. So from here, this is where it starts to get a little bit crazy. All right. What we got to do is figure out, first of all, how far is it from the Earth to the sun? The distance from the Earth to the sun is 1 AU. I don't know if you guys remember, we have talked about AUs before, but it was way back in like September, October. AU is what's called an astronomical unit. That's the distance, the average distance from the Earth to the sun. It's about 93 million miles. All right. This distance right here from the sun to the Earth is called a parsec. And that is going to be measured in not millions of miles, but light years. All right. So a minute ago, you were asking me about sine, cosine, so forth and so on. If we know this angle, right? If we know this angle, then we could use the SOHCAHTOA method. For those people who remember SOHCAHTOA, there's your angle, there's your adjacent, there's your hypotenuse, and this right here would be your distance. You have enough information here to actually figure out what the distance here, this from the sun to that star, in parsecs. Okay? And we find that angle by looking at that shift in that star. It would be 1/2 that shift. Okay. Knowing that, I'm going to tell you guys right now that if this angle is 1 degree, if this angle is 1 degree, then this distance in parsec is going to be, and I'll make sure I say this right, 3.26 light years. All right, so I'm going to write this off to the side. If the parallax, the stellar parallax angle is 1 degree, that's a 1, then the distance equals 3.26 light. LY stands for light years. Okay? That actually makes life a little easier on us. So instead of doing trigonometry and using the whole SOHCAHTOA, if I know that if 1 parsec is 3.26 light years, if 1 parsec is 3.26 light years, then I can actually figure things out a little easier. For example, that said, if we take this same distance right here, 1 AU, if this is 1 AU, so this stays the same, all right? If this object is closer, so this object is closer, what happens to this angle right here? Does the angle get larger or smaller? Take a look at this. If this is closer, will this angle get larger or smaller? Okay, I think people pointing up. Yeah, this means that if this angle right here, if this object is closer, this angle will be larger. So this what's going to mean is that if this is greater than 1, this object is closer than 3.26 light years. Okay? Once again, if I keep this same distance from the Earth to the Sun, so 1 AU, and that object is further away, then this angle right here will be smaller. So this angle will be less than 1. All right. Now that I know that information, I can simplify this lab a lot better. And we can move on to step 3. How do we calculate how many parsecs it is? It's actually pretty simple. You got to figure out the parallax angle. All right, so this angle right here. Okay, so that's the first step. The first thing you got to do is you got to calculate the parallax angle. How do you do that? Well, for the purposes of this class and the amount of time, I'm going to simplify life and just tell you guys what the parallax angle actually is. And those are going to be measured in arc seconds. Okay, so that's going to be your parallax angle. Typically what happens, real astronomers with telescopes, they're looking at this and figuring it out. They actually have a computer that does it for them. So it makes life pretty easy for them, okay? To figure out a parsec, and that's what we're trying to find out, a parsec is equal to 1 divided by the parallax angle. All right. Now I'm going to real quickly go back to our Canvas page here. And this is the lab that you guys should be working on. Let me open it up real quick here. All right. So the first 5 questions, you just simply need to follow these instructions. With you and a partner, you should be able to do that no problem. The second part, this is the part that's hard to do. Loading. All right. You can see right here, I've given you a chart, and it says Arcturus Alpha Boötis. Yes, there's a constellation called the Booties. You can giggle at that all you like. Alpha just means it's the brightest star in the constellation of the Booties. The parallax right there, I told you I was going to give you the parallax. It says that it's 0.090. All right. So if I go back to here, if I know that the parallax angle is 0.090, so this is going to be an example here. If the parallax is 0.090, now I can solve for this. I can say a parsec is 1 divided by the parallax, which is 1 divided by 0.090. And that's one I actually gave you guys on the assignment already, but I'll go ahead and calculate that on the screen so you guys can see that 1 divided by 0.090, make sure you get that decimal point in the right place, comes to 11.11. We're just going to round that off to 11. Okay? That's your parsecs. So it's 11 parsecs. Not 11 million miles or 11 light years. It's just 11 parsecs. So how do I calculate that into distance? Well, that is the 4th thing that we need to learn. To calculate the distance, remember that and if we go back to this slide right here, 1 parsec is 3.26 light years. So remember that 1 parsec equals 3.26 LY, stands for light years. From there, it gets actually pretty easy. So how many light years? The distance in light years? Well, that's going to be the parsec times 3.26 light years, which would be, in this case, in our example, your distance in light years would be equal to the parsec, that was 11, times 3.26 comes to 35.86. So the distance of this star in light years is 35.86 light years. So the distance right here would have been 35.86 light years. And that's how we determine how far away these stars. This unfortunately only works on nearby stars. Doesn't really work for far away stars because far away stars, we don't get much for stellar shifting. That's the 4 things that you guys need to know. I'll post this video on Canvas a little later if you need to go through and review it. I'll try to take a picture of these notes and maybe put it as a PDF later too. But what does it have to do with your lab? So the last thing I need to tell you guys, good news is we've got through all the hardest stuff. If you look at it right here in the lab, this goes through and briefly explains everything I showed you guys today. What I want you to do for number 6 is just briefly explain what a parsec is in anyway. And then there it is. I give you the parallax each time. Your step 3 from the notes that you took, that's how you figure out the parsecs. And once you have the parsecs, you can do step 4, that's the distance. So this is really a lot easier than it looks, okay? And then number 8, well, that comes back to step 2, trying to figure out which picture is the object closer to you. And that's it. That's the entire lab. So, oh, then one more thing. Han Solo did the Kessel run in 12 parsecs. That doesn't make any sense because a parsec is a measurement of distance. So if he's bragging about doing the Kessel run in 12 parsecs, first of all, he's using the Earth and the Sun as a reference, but second of all, he's measuring it in a distance. So I think in the later Star Wars movies, they kind of corrected it. Parsecs are not speed, it's distance. So what they said in the later ones to kind of correct that wrong science was that the Millennium Falcon did it in a shorter distance, which means he cheated. Anyway, that's it. That's what you got to do for the remainder of the class. You guys are working on that lab.